Settle down, please. So by this time, we've spent some time on rudiments of kinematics, one-dimensional motion, two-dimensional motion, as you saw in projectile. Now, an add-on over kinematics is what is referred to as constraints. So the objective of the class today is to breed familiarity with constraints of various kinds, constraints related to strings, constraints related to blocks or wedges. These are two important things that I'm going to deliver to you today. Simple stuff, but extremely important. Once you get a hang of it, you'll find no issues with it. But make sure you gather all the ideas in the class while I'm communicating. Feel free to exchange with me as and when required. Now, first things first. Suppose there are 2 points. There is a point A and there is a point B. All right. And A has coordinates x1, 0. And B has coordinates x2, 0. All right. Now, what is AB? AB is going to be x2 minus x1. AB is going to be x2 minus x1. Yes or no? Right? A and B are moving points. A and B are moving points. Let's say A has a velocity v1 to the right and B has a velocity v2 to the right. Clear? So the length AB will change with time. So the length AB will change with time in a general sense. Now, rate at which AB changes with time is given by ddt of x2 minus x1. Yes or no? That's the rate at which AB changes with time. That's the rate of change of separation AB with time, right? But this is going to be, so ddt of AB is going to be ddt of x2 minus ddt of x1. Yes or no? ddt of x2 minus ddt of x1. But what is ddt of x2? v2. Rate of change of x2 with time would give me the velocity of B along AB. That is v2. Rate of change of x1 with time would give me the velocity of A, v1. Yes or no? Right? So this is going to be v2 minus v1. Which is like rate of change of AB with time, velocity of B along AB minus velocity of A along AB. Velocity of B along AB minus velocity of A along AB is going to give me rate of change of AB with time. Yes or no? Right? Say B had a velocity 5 meters per second to the right and A had a velocity 2 meters per second to the right. Then rate at which AB changes with time is going to be 5 minus 2. 3 meters every second is how AB will change with time, right? In this case, yes or no? The important thing is you would have to deploy signs as and when required. For example, say A had a velocity 2 meters per second like this and B had a velocity 5 meters per second like this. And if I'm traveling from A to B to evaluate the rate at which AB changes with time, then I'll take velocity of B along AB minus velocity of A along AB. So in this case, the rate at which, let's say, L changes, this is L, the rate at which L changes with time is going to be given by velocity of B along AB. Velocity of B along AB is 5. Everything, if I'm going from A to B, then everything measured along AB would be positive. Everything measured opposite to AB would be negative. So dd is going to be velocity of B along AB 5 minus velocity of A along AB. Velocity of A along AB is minus 2, precisely is minus 2. So that gives me 7 meters per second. Yes or no? If dl dt turns out to be positive, if rate of change of L with time turns out to be positive, it means that L is increasing with time. If ddt of L turns out to be negative, it means L is decreasing with time. That is what it means, right? For example, say, look at this case, I revise this case. Say, B has a velocity 5 meters per second leftwards, right? Now, rate of change of AB with time in this case is going to be velocity of B along AB, which is minus 5, minus velocity of A along AB, which is 2. So that makes it minus 7 meters per second. Negative would mean that L is decreasing with time. If dl dt turns out to be positive, it means L is increasing with time. If dl dt turns out to be negative, that means L is decreasing with time. This is what it means. Clear? Now, suppose A had a velocity, say v1 like this, at an angle theta 1, and B had a velocity v2 like this at an angle theta 2, say, right? Now in this case, if I have to obtain the rate of change of L with time, say this is L, then I'll take velocity of B along AB minus velocity of A along AB. So then, what's the velocity? In this case, what is dl dt? Dl dt is going to be, I'll have to take the velocity components along AB. This time I'll have to take velocity components along AB. So this time it's going to be v2 cos theta 2 minus v1 cos theta 1. So this is going to be v2 cos theta 2 minus v1 cos theta 1. This time the velocity components along AB would have to be taken to find rate of change of L with time. Clear? AB changes only because they have different velocities along AB. Right? Now, no issues with this, right? All of you have registered all that I have said. Huh? Now, suppose there is a string. Suppose there is a string. Call this string AB. What's a string? What's the character of a string? A string is an inextensible entity. A string is characterized by its inextensibility. That's a string. A string is characterized by its inextensibility. That means the length of the string will not change. In contrast, there is a spring element. In a spring element, the length changes with time, would change, but in a string, the total length will remain the same, right? That's the difference between a string and a spring. Clear? So now we're talking of a string AB. Clear? Now, say I place two bridges, moving bridges. Say there is bridge B1 and there is bridge B2. Placed along the length of the string. Placed along the length of the string at points C and D. At points C and D. These bridges are placed. Right? Say these bridges have velocities. Say these bridges have velocities. Say the velocity of bridge 1 is V1 along the string, and the velocity of bridge 2 is V2 along the string. All right. Yes or no? Not only that, the ends of the string. Say this end of the string has a velocity u, and this end of the string has a velocity v. These are the velocities of the end of the string. Yes or no? This is a string AB, and I conceive of three segments of the string. AC is a segment, CD is another segment, and DB is a third segment of the string. Yes or no? The string has three segments by virtue of two bridges. Sometimes I'll call these bridges, or C and D I'll refer to as nodes. Nodes or bridges. Moving bridges or moving nodes. Clear? So now there are three segments in this string. AC is a segment, CD is a segment, and DB is a segment. Clear? A and C. See, this bridge is moving to the right. A is also moving to the right. So the length AC will change with time. What's the rate at which AC changes with time? V1 minus U? Yes or no? Is it not? Okay. What's the rate at which CD changes with time? V2 minus V1. What's the rate at which DB changes with time? V minus V2? Yes or no? Is it not? Right? But this length, say L1, changes with time. This length, L2 changes with time. This length, L3 changes with time. Right? But their sum remains the same. Yes or no? L1 plus L2 plus L3 will not change. Even though L1 changes with time, L2 changes with time, L3 changes with time, but L1 plus L2 plus L3 will remain constant. Yes or no? That's by virtue of inextensibility of the string. Inextensibility of the string. Inextensibility of a string is what's referred to as a string constraint. Inextensibility of a string is essentially referred to as a string constraint. Yes or no? Inextensibility of a string is referred to as a string constraint. Now, so the string constraint is essentially L1 plus L2 plus L3 equal to a constant. That's a string constraint. That's a string constraint. Yes or no? So, which would mean dL1 dt plus dL2 dt plus dL3 dt is going to be 0. Rate of change of L1 plus L2 plus L3 will be 0 because L1 plus L2 plus L3 is a constant. So rate of change of this with time is 0, but rate of change of this with time is rate of change of this with time plus rate of change of this with time plus rate of change of this with time. All of this would add up to 0. Yes or no? So do you realize this is 0? What is dL1 dt? dL1 dt is V1 minus U. Right? Rate of change of L1 with time, where I travel the string from A to B. All velocities measured in the direction of traversal of the string would be positive. All velocities measured opposite to the direction of traversal of the string would be negative. So I have a choice of traveling the string from A to B or from B to A. What I should keep in mind, what I should remember is, while I am traversing the string, write down, while traversing the string from one end to another, while traversing the string from one end to another, encountering various segments of the string, encountering various segments of the string, encountering various segments of the string, the velocities at the nodes or the bridges, the velocities at the nodes or the bridges to be taken positive in the direction of traversal, to be taken positive in the direction of traversal, and to be taken negative, opposite to the direction of traversal, opposite to the direction of traversal. So then, if I go from A to B, if I am traveling the string from A to B, so I go from A to C. So in this segment, this is the final point, this is the initial point. So I'll take velocity of the final point in the direction of traversal minus velocity of the initial point in the direction of traversal, which will give me dl1 dt. What will be dl1 dt? dl1 dt is going to be, I am traveling the string from A to B. While doing this, I take the velocity of C along AB minus velocity of A along AB. Final point minus initial point, right? For this segment, C is the final point, A is the initial point. I take the velocity of the final point in the direction of traversal minus velocity of the initial point in the direction of traversal. So from A to B, it's V1 minus U. That's dl1 dt. That's dl1 dt, rate of change of this segment with time, right? Then I go from C to D. This is the final point, this is the initial point. Then dl2 dt would be what? Velocity of the final point in the direction of traversal minus velocity of the initial point in the direction of traversal, yes or no? So that's going to give me V2 minus V1. So right, plus I take the third segment. In the third segment, I go from D to B. D is the initial point, B is the final point. So dl3 dt is going to be velocity of the final point in the direction of traversal minus velocity of the initial point in the direction of traversal. So that's going to be V minus V2. So V minus V2 is 0, Yes or no? This therefore is a kinematic representation of string constraint. This is just a representation of the fact, a kinematic representation of the fact that the string length is constant. This is just a kinematic representation of the fact that the string length is a constant, nothing else, right? Kinematically, that means in terms of the velocities of nodes or bridges that occur along the length of the string during our traversal of the string. Clear? Now, if I get this, then the same thing could have been obtained in terms of acceleration. See, if I differentiate all of this with respect to time, right? That means if I differentiate all of this, suppose the acceleration of the end A is A naught, the acceleration of C. See, these points could also be accelerated, A, C, D, etc., right? Suppose C has an acceleration A1 D has an acceleration a2 and B has an acceleration af. These are the accelerations of various points. Yes or no? Again, look at this equation. I could also differentiate this with respect to time once again. If I differentiate v1 with respect to time, what would I get? A1. If I differentiate u with respect to time, what would I get? A0. v2 with respect to time, a2. v with respect to time, af. Yes or no? So, what I have written for velocities, I could have also written for accelerations. That means the same stuff would give me, if I differentiate this with respect to time, I get a1 minus a0, a1 minus a0, differentiating this with respect to time, a2 minus a1, a2 minus a1, this with respect to time, af minus a2, af minus a2. All of this must turn out to be 0. All of this must turn out to be 0. Yes or no? That means acceleration, I traverse a string from A to B. This is one segment. Then for this segment, I take acceleration of C along AB minus acceleration of A along AB. Plus, then I come to this segment. Acceleration of D along AB minus acceleration of C along AB, which would be A2 minus A1. Then I come to this segment. Acceleration of B along AB minus acceleration of D along AB. Along with their signs, these are algebraic accelerations. If an acceleration is in the direction of traversal, positive. If an acceleration is opposite to the direction of traversal, negative. That's the rule of the game. Yes or no? Do you understand that? No issues with this? Now, let me show you how to apply all of this to real situations, to actual situations, right? And get a feel for this. Make sure that everything is registered in the class. It's a one-time effort, easy thing. And if you've understood this, you'll find this very useful. Okay? Oh, sorry. Say, I look at a fixed pulley. This is a pulley. And it's fixed. It's a fixed pulley. Okay. And say these are two ends where, say, two particles could be attached. Say there is a particle m1 attached to this end and there is a particle m2 attached to this end of the pulley. All right. Now, notice that there are three segments in the string. Three segments in the string. Say I call this end of the string A, right? This is a bridge. This is a bridge, right? I call this bridge B. This is another segment of the string. And this is a node or a bridge. This is C. And this end of the string is DC. This end of the string is DC. Clear? Now, suppose m1 has a velocity v1 upwards. And m2 has a velocity v2 downwards. Say m1 has a velocity v1 upwards, m2 has a velocity v2 downwards. What I will then have to do is, to the nodes or the bridges B and C, I will have to assign velocities, right? What's the velocity of the bridge B? 0, isn't it? It's a fixed point on the pulley. Its velocity is 0. So I would assign a 0 velocity, in the sense that the position of B, let's say with respect to the ground, is not changing with time. Position of this point is not changing with time. Yes or no? So this is going to have 0 velocity, right? C, what velocity will I assign to this? 0. And to D, the velocity assigned is v2. Then I traverse the string from A to D. I could traverse the string from A to D or D to A. It does not matter. It does not matter. From A to D, say. So, in the process, my first segment is AB. First segment is AB. I'll take velocity of B in this direction minus velocity of A in this direction. What's the velocity of B in this direction? 0. Minus velocity of A in this direction, which is V1. Right? Yes or no? Then come to this segment of the string. I'm traveling the string like this. So it's going to be 0 minus 0. It's going to be 0 minus 0. Now, look at this segment of the string. Then I go from C to D. This is my direction of traversal. So velocity of D in this direction minus velocity of C in this direction. What's the velocity of D in this direction? V2. What's the velocity of C in this direction? 0. So plus V2 minus 0. That is 0. Yes or no? Right? So this gives me very clearly V1 equal to V2. This gives me V1 equal to V2. Yes or no? That means if this point has a velocity 5 meters per second upwards, then this point will have a velocity 5 meters per second downwards. I could have got a little algebra just to demonstrate. Now one more thing. See, this middle segment is of constant length. Even though these masses move up and down, the length of BC is constant. This is the wrap-up length around the pulley. This is the wrap-up length around the pulley. So the length of this segment is constant. It does not change with time. So in writing this equation, this is the middle segment. This is the consideration for the middle segment, B to C. You can ignore the middle segment because it will have no contribution. It will have no contribution. Right now I am writing this to be formal, but over a period of time, if you find a certain segment to be of constant length anyways, then don't have to write the consideration towards that segment. This is the consideration towards the segment BC, and it could have been avoided. Right? So down the line, I will not write the equation. I'll write the expression for AB, I'll write the expression for CD, but I would choose not to deal with BC because BC is inactive in terms of participation of all of this. Right? Now, no, not in this string constant. Why would the mass play a role in all of this? These are different masses only. I'm saying if this mass had a velocity v2 downwards and this mass had a velocity v1 upwards, then what's the relationship between v1 and v2? This is the relationship between v1 and v2. You understand that? Yes or no? How to obtain v1 and v2 is different. But all that I'm saying is, if this had a velocity v1 upwards, this would have a velocity v2 downwards. And the same thing could have been said of acceleration. Suppose this had an acceleration a1 and this had an acceleration a2. downwards. Okay. Now I don't even know whether this actually is moving up and this is moving down or vice versa. But eventually when I solve for A1 and A2, and if some things turn out to be positive, then my choice of direction for that thing is right. If something turns out to be negative, that means it's just opposite to the choice of direction that I have made. That's all, right? So you can be callous in writing up, down. You could take, I'll demonstrate that in a little while. But for the time being, let me assign acceleration to the nodes. The acceleration of this node will be 0. The acceleration of this node would be 0. This would be a passive segment. I will not deal with it. And then acceleration of this is A2 downwards. So then if I have to write the string constraint while traveling from A to D, then that's going to be 0 minus A1. Right? Acceleration of this point in this direction minus acceleration of this point in this direction is going to be 0 minus A1. Right? I don't want to deal with this. This is passive. Then I go from C to D. This is the final point, this is the initial point. This is my direction of traversal. So acceleration of D in this direction minus acceleration of C in this direction. So that's going to be A2 minus 0. And all of this must add up to 0. That is out of a string constraint. And that gives me A1 equal to A2. Yes or no?
So if we take velocity or acceleration upwards as positive, downwards should...
No, it's not upward, positive, downward. I'm saying, listen to me very carefully, dude. I'm saying all velocities in the direction of traversal of the string positive, opposite to the direction of traversal of the string negative. Okay? So, let's say when I'm going from here to here, this is my direction of traversal. So velocity of B in this direction minus velocity of A in this direction. But when I'm going from C to D, my direction of traversal is positive. So all velocities and acceleration measured in this direction will be positive. All velocities and acceleration measured opposite to the direction of traversal, positive or negative. Yes or no? Got me? It's not going to be up or down. It's going to be in the direction of traversal or opposite to the direction of traversal. That's the key thing to understand here, right? Now, say just to get a little general with things, say I took this acceleration of m1 as a1 upwards, acceleration of m2 as a2 upwards. Let me see what I get out of string constraints. Let me see what I get out of a string consideration. So I go from A to B, 0 minus A1, right? Plus, I don't bother about this segment, 0, 0, right, Nilesh? Then I go from here to here. Then this is my direction of traversal. So acceleration of D in this direction minus acceleration of C in this direction. What's the acceleration of D in this direction? Minus A2, precisely, minus A2. What's the acceleration of C in this direction? 0. And that gives me A1 equal to minus A2. What does it mean? It means the accelerations of C and D are of same magnitude but in opposite direction. If one is negative of the other, it means they are in opposite directions. That means if this moves up, this moves down, or if this moves down, this moves up. This is what it means. So there is no loss of generality. Even if I got a little random with my initial choice of directions, I'm not going to lose out on the basic. Are you all okay with this or not okay? Clear? See, I'm traveling the string like this. So acceleration of B in this direction, 0. Minus acceleration of A in this direction, A1. Then I go this way. This, like I said, will be a passive element because BC is a segment whose length is not changing with time. So I will not bother about it, right? Then I go from C to D. D is my final point, C is my initial point. Acceleration of the final point in the direction of traversal minus acceleration of the initial point in the direction of traversal. Acceleration of D in this direction is going to be what? Minus A2, isn't it? If I've chosen A2 like this as the acceleration of D, then its acceleration in this direction would be minus A2? Yes or no? Is it not? Acceleration of C in this direction, 0. Got me? Now, this of course, was a very simple thing which I complicated deliberately, but because I had a bigger view to this, in order that, the same simple idea when applied to more sophisticated situations can come in handy. I've applied a sophisticated idea to a very simple thing and made it look complicated, but with a purpose. See, it's no rocket science to see one thing. For a string, you might be tempted to believe why I did all this for such a situation, because I could apply the same tenets to sophisticated situations. In the sense, for sure, if this is a fixed pulley, and if this moves up by 1 centimeter, this must move down by 1 centimeter in a given time. Yes or no? See, if this, because there is an interplay between this length of the string and this length of the string, any change here would be equally reflected in CD. If this decreases by 1 centimeter, this will increase by 1 centimeter if it's a fixed pulley, right? So, needless to say that if this had a velocity of 5 meters per second, that means this length is decreasing 5 meters every second. That means this length must increase 5 meters every second. That means D must go down by 5 meters every second. Yes or no? Right, for which I wrote all those equations, but it's about constancy of string length, which is the string constraint, which is what we are all dealing with right now. Okay, now let me make matters a little more cheesy. Okay, but so far so good, right? You've been able to understand how I deploy these expressions and equations in going from one end of the string to the other end. Right now, what I do is, let me add a little more flavor to this situation. Right now, I'm only trying to connect velocities and accelerations of different parts of the string. I'm not trying to calculate them, I'm just trying to find a relationship between velocities and accelerations of the two ends of the string, right? Which is out of a string consideration, a string constraint, constancy of string length. Now, instead of the pulley being fixed, okay, let's say the pulley is moved up with an acceleration A0. Let's say the pulley is moved up with an acceleration A0. Say this is a pulley, and the pulley is moved up with an acceleration A0. A0. Not a fixed pulley anymore. Not a fixed pulley anymore. It's a movable pulley. Clear? Say there are masses m1 and m2 attached to the ends of the string. Right? I do not know whether m1 has an upward acceleration or downward acceleration, or m2 has an upward acceleration or downward acceleration. I can be random about that choice. I don't care. Eventually, on solving equations, the appropriate sign would come and would justify everything, right? So I will not have to break my heads over the actual direction in which m1 is moving or m2 is moving. The signs will emerge on their own, telling us the direction in which m1 and m2 are respectively moving as seen by a ground observer. Right? Now, let me label the nodes here. Let me label the nodes here in this string. Say this end is A. All right. This end is B. This end is C and this end is D. How about it? Right? Let me assign acceleration to these nodes. Let me assign acceleration to these nodes. Say A1 had an acceleration, A had an acceleration A1 downwards. It could have been upwards. But then when I solve, if A1 turns out to be -3, then I know that the acceleration of A was 3 units upwards. So like I said, I'm not going to lose out on generality if my choice of direction is a little arbitrary random initially, right? And say the acceleration of D is A2 downwards. On solving for A2, if A2 turns out to be 5, then it's actually downwards. If A2 turns out to be -5, that means it's upwards. What's the problem? A1 and A2 can continue to be our algebraic tools. We will not have to break our heads over their actual direction at the very onset. Let the equations come together, connive, collaborate, synergize, and tell me the signs that A1 and A2 come with, and therefore the directions would get automatically exposed when I solve for A1 and A2, and the signs will tell me the actual directions. But at the very beginning, I don't have to bother about that, right? Now, this NB, I will have to assign an acceleration to this NB. A0, yes, this is fixed to the pulley. So if there is a ground observer, man or monkey, does not matter. He would find B to have an acceleration A0 upwards because this B is integral with the pulley. Yes or no? This point B would have an acceleration A0 upwards as seen by a ground observer. Yes or no? So what acceleration would I assign to this node? A0. Unlike the previous case where it was assigned an acceleration 0. Right? And by the way, whatever I am doing with accelerations, I could do with velocities. Right? So with B, I'm going to assign A0 upwards. Right? How about C? Upwards, precisely. C is also going to be A0 upwards. Very good. And D, of course, I have made an arbitrary random choice, A2 downwards. It's all right. I should just be consistent while writing my constraint equation. In the direction of traversal, if I take a segment, then that segment has a final point and an initial point. All velocities or accelerations measured in the direction of traversal, positive. All velocities or accelerations measured opposite to the direction of traversal of the string would be negative. Right, Pratham? Yes or no? Okay. So then I go this way. And I could have traversed this way also. There is not going to be an issue. I should just be consistent with my signs. Then any choice of direction of traversal is justified. So then when I go from A to B, this is my final point, this is my initial point. Acceleration of B in this direction minus acceleration of A in this direction. Yes or no? Right? So that's going to be A0 minus acceleration of A in this direction is going to be minus A1. Precisely. Very good. Minus A1. Plus. I don't have to bother about this fixed segment. Passive. Then I go from C to D. This is my final point. This is my initial point. So acceleration of D in this direction minus acceleration of C in this direction. Yes or no? What's the acceleration of D in this direction? A2. A2. Acceleration of C in this direction? Minus A0. Right. So acceleration of D in this direction is A2 minus acceleration of C in this direction is minus A0. And all of this must turn out to be 0. Which would give me 2A0 plus A1 plus A2 is 0. This is my constraint equation. This is my constraint equation for this system. This is the relationship that connects the acceleration of m1, the acceleration of m2, and the acceleration of the pulley. Yes or no? Clear? All's good? Right? Now, so far so good. Let me add some more juice to it then. Clear? Let me have a system in which there are two pulleys, one fixed and one movable. One fixed and one movable. Let's have that. Clear? This is a fixed pulley, but this is a movable pulley, right? This will move up and down. This is a movable pulley, this is a fixed pulley. And this is the only string that we perceive here. This is the string that we are talking of, right? We are going to deploy string constraint for this string, right? Now, say this has an acceleration a1 upwards. And by the way, again, I repeat, might have become cliched, but I want to reiterate that whatever I'm doing with accelerations, exactly the same thing I could do with velocities. Right? Say, this is my node A, and it has an acceleration a1 upwards. Right? This mass m2 at this end, say, has an acceleration a2 downwards. That means this mass is integral with the pulley, so this pulley also has an acceleration a2 downwards, yes or no? This pulley will also have an acceleration a2 downwards, right? Okay. This is B, this is C, this is D, this is E, this is F. Right? Now, these are my nodes. B, C, D, E, F are my nodes. I want to be able to deploy the string constraint equation for these nodes. So, first of all, I must assign acceleration values to these nodes. What would I assign to B? 0. This is a fixed pulley. So, B would be assigned a value 0. How about C? 0. A2 downwards. This D is integral with this pulley. This pulley has a downward acceleration A2. So D would be assigned a value A2 downwards. Very good. E would be assigned a value A2 downwards. No, A2 downwards. It's going to be A2 downwards, yes or no? If D has an acceleration A2 downwards, E will have an acceleration A2 downwards. Both will have the same acceleration downwards. They're on the same pulley. Yes or no? I'm still not traversing the string. I'm only applying acceleration values to various nodes as per an initial situation. What acceleration value will I assign to this node? 0. It's fixed to the ceiling. A fixed ceiling, right? 0. Now, time for me to go from one end A to F or F to A. Does not matter. And arrive at a relationship that will connect A1 and A2. It will connect A1 and A2. a relationship connecting A1 and A2, which would be my constraint equation. That would be my constraint equation. Now, go from A to B. 0 minus A1? 0 minus A1, yes or no? Right? Do I deal with this? No. No, I don't have to deal with this segment. Wrapped up length, it's remaining constant. Then I go from C to D. This is my direction. Velocity of D in the direction of traversal minus velocity of C in the direction of traversal. So that's going to be A2 minus 0. Right. Do I want to deal with DE, wrapped up length? No. No. And then I go from E to F. This becomes my new direction of traversal. Right? This becomes my direction of traversal. So I'll take acceleration of F in this direction minus acceleration of E in this direction. Right? What is acceleration of F in this direction? 0. What's acceleration of E in this direction? Very good. Plus 0 minus A2. And all of this must add up to 0. And whatever I have done with accelerations, I could have done with velocities. What do you say? Right. So this gives me like A1 equal to 2A2. A1 equal to 2A2. That's my constraint equation for this situation. That's my constraint equation for this situation. Right? So if this pulley is known to have an acceleration of 3 meters per second downwards, meters per second squared downwards, this would have an acceleration of 6 meters per second squared upwards. Yes or no? Clear? All's good? There is another way one could have looked at this situation. Yeah, you have a question now? No? Yeah? No? You're all doing fine with this? Let me just give you another view to this. Let me give you another view to this. Justify it with some very mundane, earthly, simple logic. A1 equal to 2A2. Let me also justify it with some very ordinary logic. Okay? Why should that be the case? Can I remove the clutter from here and redo this situation? Rehandle this situation? Without all of this? Shall we do that? This is the fixed pulley, this is the movable pulley. This is the fixed ceiling. Look at the movable pulley. Just look at the movable pulley separately. Let's look at the movable pulley separately. now this pulley, let's say, is descending downwards. Let's say this pulley is descending downwards. This is the position DE. This is the position DE. See, after a while, the pulley descends by an amount x. Let's say the pulley descends by an amount x in a certain time. That means this line DE will move down by x units. This line DE will move down by x units if the pulley has descended by x unit, right? This is x units. DE has moved down by x units. Say D prime E prime. Right? C and F are fixed points. C and F are fixed points. Yes or no? So now, as far as the pulley is concerned, there is a string to the left of the pulley, there is a string to the right of the pulley, right? Do you see then that when this pulley moves to this position, then this length increases by x units, this length increases by x units, the distance from C increases by x units, this is also x, yes or no? Right? That means this length increases by x units. If the pulley moves down by x units, the length CD increases by x units. Also, the length FE increases by x units. Right? See, so this length increases by x units, this length also increases by x units. That means this length plus this length together, they will increase by 2x units. If this increases by x units, this increases by x units, then this length plus this length, this total length increases by 2x units. Yes or no? This length plus this length will increase by 2x units. Where will it come from? It will not be generated for you, right? This length increases by 2x units because this will decrease by 2x units. Isn't it? Somewhere it has to decrease. If it increases by 2x somewhere, then it has to decrease by 2x somewhere else. Where all could it decrease by 2x? The only place it could decrease by 2x is this. That means if the pulley has moved down by x units, mass m1 must have moved up by an amount 2x units to compensate for the change in lengths, to maintain the same total length of the string. Yes or no? I will. I'm saying if the pulley moves down by an amount x units, this portion of the string increases by x units. This portion of the string also increases by x units. That means this length and this length together will increase by 2x units. If this length and this length together increase by 2x units, somewhere, some portion of the string must decrease by 2x units. Right? This is the total string. This and this portion together have increased by 2x units. That means there must be some segment that would have decreased by 2x units. Which segment could it be? It could be only this segment that could decrease by 2x units. Why? Because this segment and this segment will not change length. To maintain the same total length of the string, if this and this together have increased by 2x units, this length must decrease by 2x units. That means this must move up by 2x units. Only then this will decrease by 2x units. That means if this pulley has moved down by an amount x, this mass m must have moved up by an amount 2x. That means in the same time, if this travels 1 centimeter, this will travel 2 centimeter. That means the acceleration of this must be twice the acceleration of this. So if the acceleration of this is a downwards, the acceleration of this will be 2a upwards. The acceleration of this is going to be 2a upwards. Yes or no? All's good? Sounds fine? So this is another way you could have looked at the whole thing. Right, Hussein? Now, let me illustrate a little more. Right? say there is a fixed pulley like this. There is this end of the fixed pulley. This end of the string is connected to a movable pulley. This is a movable pulley. And say these are two masses, M1 and M2. And say this is M3. Okay. This is my movable pulley. This is my fixed pulley. Now, suppose this moves up with a velocity Vp. Algebraic, it could move up or down, that's another story, but the sign of Vp that eventually emerges will tell me whether it's moving up or moving down. I have just been arbitrary in my choice. So this moves up with a velocity Vp. Say this mass moves down with a velocity V1 and this mass moves down with a velocity V2. I want to connect Vp, V1 and V2. And again, like I said, whatever I do with velocities, I could have done with accelerations, right? Now, I want to connect Vp, V1 and V2 algebraically. I want to be able to connect Vp, V1 and V2 algebraically, right? Now, there are two strings here, two pulleys and two strings. This is one string, this is another string. To each string, the string constraint would have to be applied separately. You don't mix up string constraints for multiple strings. This time we not only have two pulleys, but we also have two strings, right? One fixed pulley, one movable pulley. Now, these are my nodes. Let's say this is my string. This is A, this is B, this node is C, and say this end is D. This end is D, which is connected to this movable pulley. Right? So since the end D of the string moves down, this pulley will also move down. Yes or no? Now one thing do you realize? If you just look at this fixed pulley, if you just look at this fixed pulley, this is M3. If this has a velocity Vp, then look at D. D will have a velocity Vp downwards. Do you believe that? Because the amount by which this will move up is the amount by which this will move down to maintain the total length of the string constant. Yes or no? So if this has a velocity Vp upwards, then the end D will have a velocity Vp downwards, right? So that means now D is integral with this pulley. So this pulley will also have a velocity Vp downwards, right? This pulley will also have a velocity Vp downwards. Yes or no? Right? Now, let me look at EF. What velocity would I assign to E? Vp downwards. Right. Vp downwards. What velocity will I assign to F? Precisely, Vp downwards. Say G and H. What velocity will I assign to G? V1 downwards. What velocity have I assigned to H? V2 downwards. Yes or no? Now, the fact that I have chosen velocity of D Vp downwards and velocity of M3 Vp upwards, I have already used up the string constraint for this string. So I don't have to bother about this string anymore. Yes or no? But I need to deploy the string constraint for this string. I could traverse the string from G to H or H to G and deploy the string constraint. Fair enough. Shall we do that then? So, let me go in this direction. G to E. This is my final point, this is my initial point. Velocity of final point in the direction of traversal minus velocity of initial point in the direction of traversal, right, Pratham? Velocity of E in this direction is what? Minus Vp. Velocity of G in this direction is minus V1. So velocity of E in the upward in the direction of traversal minus Vp minus velocity of G in this direction is minus V1. Right? Plus, do I bother about EF? No. Then I go from F to H. Then I go from F to H. Everything in the direction of traversal positive, opposite to the direction of traversal negative. Velocity of H in this direction is going to be V2. Velocity of F in this direction is going to be Vp. So it's going to be V2 minus Vp. And this must add up to 0. Yes or no? No, in the direction, this is my direction of traversal. So all velocities measured, see I'm going now from F to H. So from F to H, everything measured from F to H would be positive, opposite would be negative. This is what I want you to understand. It's not up or down, positive or negative. Things measured in the direction of traversal positive, opposite to the direction of traversal negative. So while I'm traversing the string like this, then F to H is this direction. So this direction positive. Why? When I go from F to H, this is my final point. This is my initial point, isn't it? I'm traversing the string like this. So V2 minus Vp. Clear? And all of this must add up to 0. And the same thing could be done to accelerations. Right?
So for EF, isn't it Vp plus Vp? For EF.
EF is going to be 0. This length is not changing with time, isn't it? It's going to be, this is my direction of traversal. It's going to be 0 anyways. See, if this length is not changing with time, think of it. Don't even have to deploy string constraints for that. If this length is not even changing with time, I don't have to look at considering this at all. Yes or no? Right? So this gives me Vp equal to V1 plus V2 by 2. Right? That means if this was going down with 5 meters per second, this was going down with 15 meters per second, then this would move up with 10 meters per second. 15 plus 5 by 2. All's good? Makes sense? Let me add a few more frills. Right? Let me look at a situation like this. Say m1 has an acceleration a1 to the right. Okay. m2 has an acceleration, rather a1, let me call it a1. M2 has an acceleration, say, A2 leftwards. M3, say, has an acceleration A3 downwards. M3 has an acceleration A3 downwards, say. I'm seeking to connect A1, A2 and A3. I want to be able to connect A1, A2 and A3. Right? Now, let me label the nodes. A, B, C, D, E, F, G, H. These are my nodes or bridges. I would then assign acceleration values to these bridges or nodes. Right? What would I assign to A? A1 to the right. Right? What would I assign to B? This is a fixed pulley. 0. What would I assign to C? Now, this mass is integral with this pulley. So if this mass has an acceleration A3 downwards, this pulley also has an acceleration A3 downwards. So D would have an acceleration A3 downwards. E would have an acceleration A3 downwards. Very good. F, right, good. G, 0. H would be A2 leftwards, right? Now I can traverse the string A to B to C to D to E to F to G to H and apply the string constraint right? So when I go from A to B, 0 minus A1 in the direction of traversal, positive. It's not left, right, up, down. In the direction of traversal, positive. Opposite to the direction of traversal, negative. For a given segment, I take final point minus initial point. So 0 minus A1 plus 0, and then I go from C to D. A3 minus 0, A3 minus 0, Do I bother about DE? No. Then I go from E to F. Final point, initial point. Everything measured in this direction, positive, opposite, negative. In the direction of traversal, positive, opposite to the direction of traversal. So now I go from E to F. 0 minus A3. 0 minus A3, isn't it? Because this is opposite to the direction of traversal from E to F. So minus A3. Do I bother about FG? G to H. Minus A2, minus 0. Right, very good. You've understood it now. All of this must add up to 0. The same thing could be done to velocities, right? So this gives me like, right, 2A3 is A1 plus A2. That's the relationship connecting A1, A2 and A3. That's my constraint equation for this situation. That's my constraint equation for this situation. Perfect? Let me take a situation in which a particular bridge or a node has a velocity inclined to the string. Then we'll have to take velocity components along the string, right? Let me look at a situation of that kind. say there is a fixed ceiling here and there is a ring. There is a ring. See, this is a rod, a fixed rod, and there is a ring here. Small ring, very small ring. Okay. And this ring moves in this direction with a velocity u. Now, so essentially, you know, this is almost like a point. So you could imagine this to be a point P. This is a point P moving to the right with a velocity u. Okay, almost like a ring which can slide along this in a groove. Then there is a string like this. There is a string like this, inclined at an angle theta. And at this end, there is a pulley. See, this is the pulley. This is a fixed pulley. Okay, this is a fixed pulley attached. And there is this end Q, this end Q. And this end Q has a velocity v downwards. All right. I now want to find the string constraint. I now want to find the constraint equation for this situation. I now want to be able to find the constraint equation for this situation. This is my string. This point is R, this point is S. What are my nodes? P, R, S, Q are my nodes. P has a velocity u to the right. Q has a velocity v along the string. But what velocity of P would be relevant? U cos theta. That's the velocity of P along the string. I'll have to take the velocity of nodes or bridges along the string when I write my string constraint, right? So velocity of P along the string, that's going to be u cos theta R 0, S 0, Q V downwards. Now I traverse the string from P to R to S to Q. This is my first segment. 0 minus u cos theta. Plus. This is a fixed length. I don't bother about RS, the wrap-up length, right? And then I go from S to Q. V minus 0. Equal to 0. So V turns out to be u cos theta. The problem that you showed me last time, now you go back and do all this, it'll work. All's fine. Now, we've got the idea. Let me give you one more illustration to get a superior feel for things. Right? But so far so good, right? Say there is a block like this. Movable block. Movable block. There is a fixed pulley. There is a fixed pulley. One end connected to this block. Say there is another movable pulley. The overhanging part of the thread connected to another pulley. This free end of this thread connected to another pulley. There is a string like this, there is a string like this. This is another thread, and the free end of this thread, let's say, connected to a third pulley. And then there is a string, there is a free end like this. This is my system. This is my system of 3 pulleys. One fixed pulley. This is my fixed pulley. The other 2 movable pulleys. This is a movable block. Say this end, this free end, is pulled down with an acceleration A. This free end is pulled down with an acceleration A. You would expect the block to move up. You would then expect the block to move up. Let's say the block moves up with an acceleration A0. Let's say the block moves up with an acceleration A0. Clear? I want to find a relationship between A0 and A. There are multiple pulleys and there are multiple strings here. And I would have to draw string compliance with each of the string. Now, let me look at this pulley, this top pulley. Let me label the points. Say this is A, this is B, this is C, and this is D. Right? Let me call it O. Now, if you look at this fixed pulley, if this end of this fixed pulley, just look at this pulley, is moving up with an acceleration A0, then O would have a downward acceleration A0, yes or no? Isn't it? The point O, this free end would have a downward acceleration A0, yes or no? Right? That means this pulley would have a downward acceleration A0. Let's say this is pulley 1, this is pulley 2, this is pulley 3. Right? This pulley 2 would have a downward acceleration A0. Right? So if you look at pulley 2, this is pulley 2. Let me call it P, Q, R. And say this is O prime. This pulley 2 has a downward acceleration A0. This is P, this is Q, this is R, and this is O prime. This is O prime. Right? P has an upward acceleration A0 because it is integral with the block. So P has an upward acceleration A0. Q and R are integral with this pulley. So if O has a downward acceleration, isn't it? O has a downward acceleration A0. So Q and R will have downward accelerations A0, right? So Q has a downward acceleration A0. R would also have a downward acceleration A0. Yes or no? Shall I repeat, or are you okay with this? Perfectly all right? Suppose O prime, this end O prime, has an acceleration A2 downwards. Has an acceleration A2 downwards. Let me find A2 in terms of A0. Let me find A2 in terms of A0, and how do I do that? By deploying the string constraint, traveling from one end of the string to the other end, maintaining consistency of signs. P is connected to this block. So if this block has an acceleration a naught, then all points on this block will have an acceleration a naught. Yes or no? Isn't it? If this pen is moving up with an acceleration a naught horizontally, then every point on this will have an acceleration a naught upwards. Yes or no? Clear, no? In fact, even this point will have an acceleration a naught upwards. Right? Okay. So let me apply string constraint to obtain the value of a2. Okay. Going this way. From P to Q. Minus a naught. Minus a naught. Do I bother about QR? No. Then from R to O prime. A2 minus a naught. Right? And all of this must add up to 0. So this gives me a2 equal to 3a naught. Yes or no? That means this pulley 2 is moving down with an acceleration 3a naught. This pulley 2 is moving down with an acceleration 3a naught. Right? So a2 turns out to be 3a naught. That means this pulley is moving down with an acceleration 3a naught. Yes or no? I'm sorry. O prime. I'm so sorry. O prime is moving down with an acceleration 3a naught. I'm so sorry. Let me stand corrected. O prime has a downward acceleration a2, which is 3a naught. And if O prime has a downward acceleration 3a naught, that means this pulley 3 is moving down with an acceleration 3a naught. Yes or no? Pulley 3 has a downward acceleration 3a naught. Clear? Okay. Now let me shift the load to pulley 3. Let me apply string constraint to this final string. Clear? So let me move to pulley 3. Given that O prime has a downward acceleration 3a naught. That means pulley 3 has a downward acceleration 3a naught. Right? Pulley 3 this time. Pulley 3. Say this end is S and this end is T. This end is T. Okay. Pulley 3. This is O prime, the center of this pulley. This pulley, along with O prime and all other points, is moving down with an acceleration 3a naught. This is the end S. S has an upward acceleration a naught because it's integral with the block. This point, see this point, if this pulley has an acceleration 3a naught downwards, then this point will have an acceleration 3a naught downwards. This point would have an acceleration 3a naught downwards. This part of the string, the final free length. This is T. T has an acceleration a downwards. I have to obtain a in terms of a naught. This is my final pulley and my grand finale for the string constraint. Okay. So let me traverse the string from one end to another and apply string constraint. So I go along this. From here to here, minus 3a naught, minus a naught. Yes or no? A naught. That is for this segment, having traversed this way. Do I bother about this segment? No. Then I go this way. A minus 3a naught, right? All of this must add up to 0. Right? And this gives me a equal to 7a naught. Right? So if a naught was 1 meter per second, the acceleration of this end would be 7 meters. If this was 1 meters per second squared, this would be 7 meters per second squared downwards. By this time, you feel mentally comfortable with string constraints, right? You've assimilated the basic idea. Clear? No issues with this? Right? Now, another constraint which we are going to encounter. All this was a string constraint. All this was a string constraint. Then I'm going to teach you what's called a wedge constraint. A wedge constraint. A wedge constraint. No, any string. I've deliberately dealt with police because you're going to encounter a large number of situations related to police. I've just used that as my mouthpiece. But a string length will remain the same, whether pulley or no pulley. Right? The string length will not change. So the same idea could be applied to any diverse situation. Now a wedge constraint. Now what is it that I mean by a wedge constraint? Say if this is a wedge, we will look upon a wedge as a block or a non-deformable entity. We will look upon this as a non-deformable entity. Like the string was inextensible, this would be non-deformable. This would be non-deformable. Right? Now suppose this was a certain wedge. First of all, let me define what's called a normal to a wedge. Say if this was a surface, then the normal to this surface is this. This is a normal to the surface. Perpendicular to the surface is a normal to the surface. This will be a tangent to the surface. Parallel to the surface is the tangential direction. Perpendicular to the surface is a normal direction. If there is a curved surface like this, if this is a curved surface, then at a given point P, this is the tangential direction. This is the tangential direction. Perpendicular to the tangential direction, this then would be the normal direction. This would be the normal direction. Tangential direction and normal direction. Right? Now, this is one surface. This is one wedge. And say it's in contact with another wedge. So this is another wedge. Now one thing from very simple considerations. Say these are two surfaces. These are two surfaces. Okay? If they have relative motion in this direction, assume they are very long, they don't lose contact. What is this direction? Tangential direction, isn't it? This is the tangential direction. This will be the normal direction. This would be perpendicular to the surface. right? So this direction would be the normal direction, this direction would be the tangential direction, and this would be the normal direction, right? Yes or no? Relative motion in this direction will not result in loss of contact, right? But if in this direction they have different velocities or different accelerations in the normal direction, it would result in loss of contact. What I mean is, say this was one surface, this was another surface. This is the normal direction, this is the normal direction, common normal direction, commonly referred to as the common normal direction. Common normal direction for the two surfaces. These are two surfaces in contact. This is the common normal direction. This is the tangential direction, right? This is the tangential direction, or sometimes also referred to as the parallel direction. Right? Now, if this has a velocity v1 like this in the tangential direction, and this has a velocity v2 like this in the tangential direction. Assume they are very long. Assume the load surface is very long. Then they will not lose contact. Will they lose contact? If they have different velocities in the tangential direction, there would be no loss of contact. And unless this falls over this, that's another story. But different velocities or different accelerations in the tangential direction will not result in loss of contact. Yes or no? Do you understand what I'm saying? But suppose this had a velocity, this surface connected with this body had a velocity 5 meters per second like this in the common normal direction, and this surface in the common normal direction had a velocity 3 meters per second. Will there be loss of contact? Right? So two bodies will lose contact if they have different velocities and different accelerations in the common normal direction. Make a note of it. Two bodies will lose contact. Two bodies will lose contact if they had different velocities slash accelerations, different velocities slash accelerations in the common normal direction, That means for two bodies to maintain contact, or two surfaces to maintain contact, bodies or surfaces, for two bodies or two surfaces to maintain contact, their velocities slash accelerations in the common normal direction must be the same. Their velocities slash accelerations in the common normal direction must be the same. That means their relative velocity along the common normal direction must be 0. Their relative acceleration along the common normal direction must be 0 in order that they could maintain contact. Yes or no? You know what I'm saying? Right? Say, for example, this body, this top one has, and say this is the common normal direction. Okay? Isn't it? This is the tangential direction and this would be the normal direction. Rudra. Now, suppose this body 1, this is body 1, surface associated with body 1 had an acceleration a1 that it made, a1 making an angle theta with the common normal direction. This is the acceleration of 1 making an angle theta with the common normal direction, right? Whereas this surface, surface 2, that means this body, let's say this body 2, had an acceleration a2, making an angle alpha with the common normal direction. This body 2 has an acceleration a2, making an angle alpha with the common normal direction. This body 1 has an acceleration a1, making an angle theta with the common normal direction. Right? Clear? Now, for them to maintain contact, what is required? Acceleration of 1 along the common normal must be the same as acceleration of 2 along the common normal in order that they could maintain contact. Right? Along the common normal, they must have the same velocity, they must have the same acceleration in order that they could maintain contact. That means, what's the velocity of 1 in the common normal direction or acceleration of 1 in the common normal direction? A1 cos theta. What's the acceleration of 2 in the common normal direction? A2 cos alpha. This then would be my wedge constraint. This then would be my wedge constraints. And whatever I've done with accelerations, I could have done with velocities. So this then becomes the wedge constraint. A1 cos theta is A2 cos alpha. That's the wedge constraint. Along the common normal, they must have the same velocities. Along the common normal, they must have the same accelerations in order that they could maintain contact. Clear? Say, for example, this entity is called an inclined plane, right? All of you know this? This is an inclined plane. And say there is a rod, vertical rod. It is constrained to move in a groove, a vertical groove. This rod can only move vertically. This rod can move only vertically. Okay, there is a vertical rod. And it's in contact at the point P of this inclined plane. Right? Now, in this case, there is one rod and one surface. The common normal will be the normal to the surface. Would be the normal to the surface. Say, someone told you that the inclined plane had an acceleration a0 to the right. Suppose someone told you that the inclined plane has an acceleration a0 to the right. Now this is a vertical rod. Because of this groove, it is constrained to move only vertically. It's constrained to move only vertically. Very clearly, if this moves to the right, P will fall downwards, the rod will fall downwards, the rod will have a downward acceleration, yes or no? The rod will have a downward acceleration. Let's say the acceleration of the rod is A, downwards. Now, I want to find a relationship connecting A0 and A so that contact is maintained. So that contact is maintained. Right? This point, now this is the common normal direction. The normal to the surface is the common normal direction. Along this direction, in order that contact is maintained, in this direction, they must have the same acceleration, right? This is the point P. This is the point P. Now, this angle is theta. the rod, this point P shares a common, this point P on the rod will have an acceleration A downwards. The rod has an acceleration A downwards, right? The inclined plane has an acceleration A naught to the right. This angle is theta, corresponding angles, right? This is 90 minus theta, so this angle is going to be theta. This is the acceleration of the rod, this is the acceleration of the inclined plane, and this is the common normal direction. This is the common normal direction. Along, in order that they could maintain contact, what is required? Along the common normal, they must have the same acceleration, same velocity. Now, what's the acceleration of A in the common normal direction? A cos theta. Acceleration of the rod in the common normal direction is A cos theta. What's the acceleration of the inclined plane in the common normal direction? A naught sine theta, precisely. That gives me A equal to A naught tan theta A equal to A naught tan theta. So if A naught is known to me, the acceleration of the inclined plane, then the acceleration of the rod vertically is given by A naught tan theta. This is one application of a wedge constraint. Right?
So the acceleration of the rod will be G.
No, why should it be G? If it was only falling freely, if there was no inclined plane, if it was falling freely, it will be G. Otherwise, why will it be G? Isn't it? The inclined plane will exert a force on the rod, right? It will not be G. If it was free to fall, then it will be G. But it's not freely falling, isn't it? Huh? You understand the wedge constraint, therefore? Another constraint is what's called a rigid body constraint. A rigid body constraint. What's a rigid body? What's a rigid body? Yeah, in a kinematic sense, if you take any 2 points on a rigid body, then the separation between these 2 points is not going to change with time. That's a rigid body, right? So, which means, if this is a rigid body, if this is a rigid body, if this is a rigid body, and I take any 2 points on the rigid body, say A and B, and the rigid body could be moving in a very complicated manner. These are any 2 points marked on the rigid body. And this is the line joining any 2 points on the rigid body. And say, if at a certain instant of time, A has a velocity VA, making an angle alpha with AB, and B has a velocity, say V2, VB, making an angle beta with AB. Now, realize that the separation between A and B should not change with time. Separation between A and B should not change with time. That means the relative velocity along AB must be 0. Then the relative separation will remain constant. What's the relative separation between A and B? AB. When would relative separation remain constant? When relative velocity along the line joining them is 0. That means if the velocity of A in this direction is the same as velocity of B in this direction, then AB will remain constant? Yes or no? That means what we require is VA cos alpha equals VB cos beta. That means velocity of A along AB must be the same as velocity of B along AB, so that the length AB remains constant. The separation between any two particles in a rigid body must remain constant, right? Is it not? A very simple application of this fact. Can I wipe this off? Have you settled to this thought? Say there is a rigid ladder. There is a rigid ladder. AB. AB is a rigid ladder which can slide along the floor and the wall. Right? At a certain instant, say, the ladder makes an angle theta with the horizontal. At a certain instant, the ladder makes an angle theta with the horizontal. And say, this is also theta. A is given a velocity VA to the right. A is pulled rightwards with a velocity VA. A is pulled rightwards with a velocity VA. I want to find the velocity of B. The ladder is assumed to be rigid. Clear? Now, B is only constrained to move along the wall. So, velocity of B must be along the wall only, some VB, and I want to find the value of VB. I want to be able to find the value of VB. Given VA and theta, I want to be able to find VB. Now, if this is theta, this angle is 90 minus theta. Now, the separation between A and B cannot change with time. That means velocity of B in this direction must be the same as velocity of A in this direction. Yes or no? Right? What's the velocity of B in this direction? VB cos 90 minus theta. What's the velocity of A in this direction? VA cos theta. VA cos theta. That gives me VB sin theta equal to VA cos theta, or VB equal to VA cot theta. That's an illustration of a rigid body constraint. A rigid body constraint.